Geometry 10.1 Introduction to Circles. By the end of this lesson, you should be able to identify parts of circles, and you should also be able to identify lines and segments related to circles. To begin, we first need to even talk about what a circle is and special parts of circles. A circle is a set of all points in a plane that are equidistant from a given point called the center. And oftentimes we use a compass to draw circles, and it shows us exactly what we're talking about here. So if you have some center, and that's usually formed by the tip of that compass, and you are drawing all points that are the same distance away, then you've drawn a circle. Now, there's special parts of the circle. One of those special parts of the circle is the radius. And the radius is going to be the distance that's formed from the center of the circle to a point that's on the circle. So just some distance from here to here. We'll call that the radius. Now, another distance that we often talk about is the diameter. And the diameter is the distance across the circle, but it has to be passing through the center of the circle. So if I'm talking about this distance here, that's the diameter. Now, oftentimes when we talk about the radius and diameter, we're talking about the segments, and it's true. The segments are also called the radius and the diameter of the circle, if they fulfill those things. So we have the radius, that's going to be a segment that starts at the center of the circle and ends on the circle, and our diameter is going to have both endpoints on the circle, but it's going to pass through the center. Some other types of segments and lines related to the circle are a chord. Now, a chord is going to be a segment whose endpoints are on a circle. And I'm going to just name these A and B. If you're naming a chord, you'd name it just like you'd name any other segment. AB with a line segment above it. If you noticed, when we talked about the diameter, we said the diameter also had its endpoints on the circle. So we can say that the diameter is a special type of chord. Another type of line that is related to the circle is a secant. And the secant is going to pass through the circle, and it's going to have its endpoints on the circle at 2 points. So these 2 points on the circle, and the line is going to pass through the circle, and that line is going to be called the secant. We would name this just like we would name any other line with 2 points that are on it and the line symbol above it. We also have what's called the tangent. And the tangent is a line that passes alongside the circle and intersects the circle at 1 point. This point that it intersects at is called the point of tangency, and it's only going to intersect the circle at exactly 1 point. If we wanted to name this, we'd sometimes see the cursive letter, and we can call this line L, or we'd have some other endpoint that we could use to name this line. So we would name it line EF. Let's practice some of this. So we need to be able to determine by looking at this diagram whether the line or segment is best described as a chord, secant, tangent, diameter, or a radius. In our first one we have segment CG. It's going to be really important that in this chapter you pay attention to the symbols that are above the notation because there can be subtle differences, and it'd be the difference between a secant and a chord. You need to pay attention to that. So here we have segment CG. And segment CG begins at the center of the circle and ends on a point on the circle. So that's best described as a radius of the circle. Our next one, segment EG, has 2 endpoints on the circle. And a segment that has both endpoints on the circle is a chord. But what we'll notice is that this passes through the center of the circle. So we're going to call this a diameter. And last we have line AD. Line AD appears to go alongside the circle and intersect the circle at 1 point. And so the best way to describe this is as a tangent. We're going to have some theorems that have to do with tangents, and we'll talk about that later. But first, I want us to think about different ways that two circles can intersect. And we can think of them as two circles intersecting, and they'll have 2 points of intersection. They can also intersect to where they have 1 point of intersection, whether it's inside one another or not. And we can also have it where the circles just never intersect, and they'd have 0 points of intersection. Now, looking at some of these circles and the way that they intersect, you can have common tangents, which pretty much just means that you have a line or segment that's tangent to 2 coplanar circles. So it's going to be tangent to them at the same time. And let's take a look here. We have 2 types of common tangents. One of them could be a common internal tangent, which means that it's going to pass in between the 2 circles, and it's going to intersect them each at just 1 point. So that's one way that you can see a common internal tangent. You might also see it something like this, to where it's still in between the 2 circles, but it only intersects the circles at 1 point. External tangents are not going to go in between the 2 circles, but they will still be tangent to both of them. So a common external tangent for this last example would be something along this. It doesn't separate the 2 circles, but it is still tangent to both of them. A couple theorems that we have about tangents are these. And if a line is tangent to a circle, then it's perpendicular to the radius drawn from the point of tangency. So here we see line L, and it's intersecting circle Q at 1 point, and QP is the radius, which means we'll be able to say that QP is perpendicular to line L. The converse of this is also true. So if you notice that in a plane, you have some line that's perpendicular to the radius of a circle, and it's only intersecting here, then it's going to be tangent to the circle. So here we could say line L is tangent to circle Q. This is how you're going to write circle Q. Circle is going to be the symbol of a circle with the center drawn in, and then you're going to name it by whatever letter represents the center of the circle. So since the center is Q, we're going to call this circle Q. Let's practice this. You're standing at R, which is 4 feet away from a fountain. The distance from you to a point of tangency is 8 feet. What's the radius of the fountain? Looking at this, I notice that we formed some sort of triangle. And we know that this segment QR is tangent because the distance from you to a point of tangency is 8 feet. So going back to our last theorem, we know that if a line is tangent to a circle, then it's going to be perpendicular to the radius. So what this means is we have a right triangle. And thinking back to our last chapter on right triangles, you can use the Pythagorean theorem in order to solve for R. Our C, or our hypotenuse, is going to be this side PR. And so when we write this as C squared is equal to A squared plus B squared, C is going to be written as R plus 4, because it's this entire segment. So R plus 4 squared will be equal to R squared plus 8 squared. When you're squaring this term, you're going to need to make sure that you remember it's just like writing it twice, and so we're going to have to distribute both terms from the first binomial to the second one. So when we do that, this is going to look like R squared plus 4R plus 4R plus 16 is equal to R squared plus 64. When we simplify both sides and clean this up a bit, we have R squared plus 8R plus 16 is equal to R squared plus 64. Now looking at this, I have an R squared term as well as an R term, which sometimes means that we're going to have to use our quadratic formula. But lucky for us, when I start to solve this, I notice that my r squareds will cancel out, because as I subtract it from one side, it cancels, and all that I'm left with is 8r plus 16 is equal to 64. So then we're just going to subtract 16 from both sides, and I have 8r is 48. And then when we divide both sides by 8, we get r is equal to 6. So what is the radius of the fountain? We can say the radius of the fountain is 6 feet. We have one last theorem that we're going to get to that has to do with tangents. And it's if two segments from the same exterior point are tangent to the circle, they are congruent. So if we notice that these two tangents intersect at some point, then we can say that these segments here and here are congruent. So segment RS will be congruent to TS. And let's practice that. Here we're given that AB is going to be tangent to circle C at this point, and we also know that AD is tangent to circle C at D, which means then they both intersect at this point A. Now they're asking us to find the value of x, and from our last theorem that we just talked about, we know that these two segments are going to have to be congruent, which means in order to solve for x, we can just set them equal to one another. So x squared plus 24 will be equal to 49. We'll subtract 24 from both sides, and we have x squared is going to be equal to 25. So to solve, we will need to square root both sides, and we have x is equal to, really it's plus or minus 5, but remember, which one of these is going to make sense for us? And the only one that's going to make sense is the positive value, because we can't have negative measures. So what we'll say is x is equal to 5, and that is your final answer. And that's it. It's a lot of information, so hopefully you took plenty of notes and you'll bring those to class and use those when we practice this more in class. But that means it's time for our joke. So what do you get when you cross geometry with McDonald's? You get a plain cheeseburger.